Ta-da. Okay. Yeah, accomplishment. So I'm the alternate for this slot. I'm going to be talking about Android application security pitfalls because that's apparently all I talk about anymore is Android application security and stuff. So hopefully you'll get something out of this, even if you were here for Ryan Permy's talk. So I'm Zach Lanier. I work for Accumount Labs as a senior research consultant, which is a fancy way of saying we hack on, weird stuff. I'm also the CH in Team Jack, which is John Overhide's the JO, and we do a lot of stuff around Android security. I'm a net web mobile app pen tester type from Yore, and I've gotten into mobile stuff a few years ago. So that's my old company, so ignore that. So me flipping too fast. So we're going to talk a little bit about Android just to set the stage in case you don't know anything about Android. I assume that some people are just now getting into mobile and may have an Android device but don't know the internals about it. So then we'll talk a little bit about app distribution and just set the stage for some things. Did I cut out? Okay. Talk a little bit about how apps work, and then actually dive into issues, things that I've seen in testing Android applications, and as well as some solutions or recommendations around fixing those issues, and then finally conclusion. So what is Android inside its bender? So it's typically, most Android devices are on ARM, have ARM cores. Whatever system on chip that they're on is almost always going to be ARM. There are some x86 boxes out there running Android, but by and large, most things you're going to come across run on ARM. Older versions of Android are built on the Linux 2.6.3x series kernel. Newer ones are built on 3.0, so ice cream sandwich and jelly bean and whatnot. It's built on a series of native libraries. Your libc, which in this case is actually Bionic, which presents some differences in things that are included because it's BSD libc, not glibc. WebKit, which is always bug-free. OpenSSL, so forth and so on. The Android runtime is composed primarily of the Dalvik virtual machine, which, although applications are written in Java mostly, they're actually converted into a different bytecode format called Dalvik executable, or DEX. And the Dalvik VM is register-based, not stack-based VM versus, say, the Java VM. So this presents interesting issues sometimes around reverse engineering. Applications obviously run inside the Dalvik virtual machine, and it's basically a one-to-one process mapping for every time you run an Android application, you will see a unique process entry for it in Linux's process table. So this is the obligatory Android stack, going down to special kernel drivers that Android wrote, or that Google and the Android team wrote. So there's some deviation from your regular, your normal vanilla Linux. So quick overview of that. Big thing that people complain about with Android is this version fragmentation. As of April 2nd, this is the most current data. There are a lot of choke points here. Carriers, OEMs, carriers might be the choke point to push out over-the-air updates for whatever reason, planned obsolescence or acceptance testing. They won't push out updates, and we end up with this nice fragmented pie chart. There is a thing called CTS, Compatibility Test Suite, that Android subjects OEMs to, and part of that includes security tests, so that in order for a device to be licensed, quote-unquote licensed, there's no licensing fee, to be licensed to use Android, they have to meet the CTS tests, and some of those have making sure that file permissions are sane, and that there aren't massively privileged applications, things like that. But you'll see in this chart, 2.3 to 2.3.2 is, well, it's actually 2.3.3 to 2.3.7 is a very significant chunk of this chart, and those are your gingerbread devices that won't, necessarily receive kernel patches because they're not getting updated versions of Android, which means that combined with complete lack of mitigations, chance for, nice privilege escalations. Anyway, sandboxing on Android is not really sandboxing. It's not like iOS where there's an actual, like seatbelt on iOS actually enforces a more mandatory access control type sandbox, where on Android it's simply assigning an application and the processes associated with it a unique user ID and group ID, and then assigning really tighter file permissions so that apps can't clobber each other's data on the file system. And interaction between these things and API and programmatic access are enforced by the Android runtime based on UID and GID and some other things. So you'll see here up at the top each you'll see here in the data directory where apps store their data. Each one of these packages, data directories, have a unique user ID and group ID assigned to them, and the permissions are such that only this user ID can write this, and only this group ID is the only other thing that can read this. So that prevents App 3 from clobbering App 7's stuff. And we can see files that are created in those subdirectories, like the databases directory for this crypt SQL package has access such that only App 44 can read and write. So a slight deviation about exploit mitigations in Android. Older exploit mitigations were pretty much non-existent. We actually did have, your chance for vanilla stack-based buffer overflows. The stack between these two runs was randomized, but is still writable and executable. And the mmap section where files are mapped into memory and things like libraries as well, and the heap and the base address of the target executable, the target binary, were not randomized, so your ret to libc attacks still worked. In Android 2.3, they introduced an actual non-executable stack and a non-executable heap. So that's one step further, except that they still didn't do randomization of some other things. In Ice Cream Sandwich, they added partial or better, slightly better ASLR, address space layout randomization. So here is between these two runs of just looking at memory maps for a given process. The mmap section, where say these libraries are mapped, is random between two runs. The linker, however, is not, and the stack is also random, and the base address of the binary is not. So then finally, they did full ASLR along with other things to help randomize, further randomize memory with things like position-independent executables, strengthening ASLR, doing things like rel row and bind now to reorder sections in a program to make it even harder to predict, to reorder sections of a program so that it was more difficult to find usable addresses, as well as set to read only. Cutting out, I think. Set table to read only to make overriding entries in there difficult. So like overriding sprintf to step thing. As bind now also by resolving the location of functions at runtime rather than at when that function was called. So we can also see that, where are we? So this is actually this is a version of Android that runs Linux kernel 3. We see here that the base address is randomized. We see that the linker base is randomized. The mmap section where a library has been loaded is randomized. The heap is randomized. The stack is randomized, and they're not executable. They also added a couple of other things, dmessage restrict, which was if you've ever run like the dmessage command on a Unix box, it spits out a bunch of log information from the system. Dmessage restrict helped prevent leakage of certain bits of kernel information that could be useful in exploit development, as well as added in k-pointer restrict, which made it more difficult to find symbols in kernel memory that would be useful in kernel privilege escalations. So, like cat proc kall sims no longer leaks anything. There's weak ASLR in something like Zygote because there's this shared pool of memory across every process that gets spawned from Zygote. Zygote's the thing that starts an application when you launch it and starts the Dalvik VM and loads everything that it needs to. But for performance reasons, certain libraries and classes and things of that nature are shared across all processes. So, go explore that. Not necessarily realistic. I know there's like red text down here that's a little more difficult to read, but it says 32-bit ASLR on a long enough timeline. If you have a lot of patience, you could brute force an address, and this stuff doesn't necessarily apply to like heap exploitation or anything. Future mitigations that are probably never going to happen. Android could implement code signing enforcement so that apps that are signed, that's the only code running in memory, and it can't go fetch additional libraries from the internet and load them, which happens. Maybe hardening some of the system libraries that are included, like Bionic. There are still some versions of Android out there that don't have, compiler and linker mitigations haven't been considered for the libraries that everything's built on, like building bricks on sand. And then finally, SE Android, which is slowly making its way into the mainstream, which is a mandatory access control system for Linux, being ported to Android. The Samsung Galaxy S4, I believe, actually uses SE Android. So there's a production device out there that uses that. So, app overview. Applications have to be signed. They can be self-signed by a developer. There's no CA. There's no certificate validation chain. There's no code signing enforcement or anything like that. Anyone can sign up for the Google Play or Android market and publish applications. They do some dynamic app analysis via Bouncer, but it has actually been defeated through. It's actually just a QEMU instance that they instrument, and it's really easy to detect that you're in there and make your malware act differently. So apps are really just in an APK, which is a glorified zip file, which has, amongst other things, classes.dex, which is the Dalvik executable bytecode compiled with a bunch of, the code itself as well as a bunch of other data. And the manifest, which defines a lot of things about the application, which we'll see here in a second. Any additional resources like images, layout files to tell where UI elements need to go. Any supporting native libraries, you can use JNI to call into native code in Android. You see this especially for antivirus applications or any game application that uses really, accelerated or fancy graphics or anything like that. And then graphic signature files that just have the, the digests for all the files that are in there to make sure that it's been tampered with. So the manifest, every application, even if it doesn't have something the user interacts with, needs to have a manifest which defines the target version of Android that it's built for, any minimum requirements, as well as activities, which are the UI panes that the user interacts with, and any intent filters, which we'll discuss intents a little bit later, but just defines what types of messages it will respond to via IPC. And also, finally, perhaps most importantly, and other things, but permissions, which the capabilities that the application is actually requesting. That's probably one of the more important things if you're looking at these next to intents. So permissions, you've seen this screen before. When you go and install an application, you get prompted to install it, and it wants all these permissions, and you either say OK or cancel. So things like making a phone call, reading an SMS, writing an SMS, vibrating the phone, opening up a socket, which we just see as network communications, and accessing various bits of data. Permissions are typically enforced at a high level for programmatic things like accessing contacts or accessing SMS messages or what have you. But there are certain things that are enforced within the kernel based on group membership, for instance. So android.permission.internet actually instructs the system, the package manager instructs the system to add the user ID for the application into a supplemental group 3003, which is the INET group, which allows that user to create arbitrary, just open sockets, basically, and have network access. Then there are some other things like there are groups for accessing external storage of the SD card because that particular mount point is set that only the groups, the group members of that group can actually read and write that mount point. So permissions are not terribly granular in the sense that you could say limit an application to only talking to a certain remote host. It either has doesn't. This could be solved by SE Android, but probably complexity and the battery. So again, the Dalvik VM is not really a sandbox. Pop out of the Dalvik virtual machine with just native code. You're still only limited to whatever privileges that particular UID has, but whatever. And again, Android doesn't enforce code signing like iOS, so native code can just be fetched remotely from the internet and loaded. So, the thing you're probably more interested in. Common issues, again, kind of things that I've seen over the past few years. So, permissions issues, over-granting or under-granting of permissions, insecure transmission of sensitive data, insecure storage, information leakage through log buffers, API issues, and then, although we won't have time to really dive into Flash or WebKit or whatever, inheritance of bugs. If the framework that something is built on is buggy, then just kick the sand out from under the bricks. So permissions in brief. I mentioned that there are permissions like internet, send SMS, read contacts, etc. These are granted at application install time, which is the thing that installs packages and talks to other components to set up the file system for the app and everything. They're actually checked at the time that the time of a function or method call. That includes things like creating a socket object, accessing Bluetooth functionality, reading or writing data to or from a content provider, which is could be anything on the back end, but just serves data up in a normalized way. Sometimes at a lower level, these checks for these permissions are done they're done in a variety of ways, sometimes inconsistently and in ways that might lead developers to not understand what permissions they really need. So we already saw that slide. So I did some research with a colleague at Veracode last year, where I previously worked, on mapping out Android permissions and their requirements and the ways they were being checked across the Android API and different versions of the Android API. So as it turns out, the reference documentation includes most permission requirements for various parts of the API, but it's not 100% or 100% accurate. So this leads to undergranting of permissions or privileges, which could be a reliability issue if something is called and the caller doesn't have permissions for it. A security exception is thrown, and the application most likely crashes. Just annoys users. And then there's overgranting, where because of not understanding what the requirements really are, permission requirements are, developers just throw all the permissions at the application to get these errors to stop popping up. So it's sort of like if that was a buggy application in some other way, a malicious application could take advantage of whatever that bug is and inherit the permissions of that target application. Think AV apps, for instance. So here's an example of the documentation doesn't match what is actually happening. So for the Wi-Fi manager class, the start scan method, which is a fairly innocuous method, it's not really damning or anything, doesn't actually list the permission requirements for start scan in the documentation. That doesn't say anything about it. So actually looking at the source code for the Android API, we see that there is enforce access permission and enforce change permission, which look to see if the caller has access Wi-Fi state or change Wi-Fi state when they call start scan. And that's verified by the tool that we used at Veracode as a proof of concept to basically look and see in what class, what method, what permission was being checked, and how it was being checked. So the documentation match the reality. And people would call this, the app would crash, whatever. Same thing with telephony manager. This for the get neighboring cell info method, we see that in the documentation it says that access course updates is the required permission. And this has been reported numerous times that this permission doesn't actually exist. There is no access course updates permission, and I don't know if there ever was. As it turns out, they are actually, and there's even a comment in the source code that says, "Oh, access course updates." But looking at where, through a few levels, where this actually gets checked, it's access find location or access course location, and that's checked via enforce calling yourself permission. So, and here's the output from the tool that in fact says get neighboring cell info requires one of these two permissions, not this non-existent permission. So this just leads to developers having absolutely no idea what to do and just throwing all the permissions at the error so it goes away. So insecure transmissions, you know this one, stuff gets sent in the clear. It still happens. Again, sorry for the font, but weakly encrypted data in transit, not encrypting it at all, or passing authorization material even though the login process was encrypted, ignoring certificate validation errors, not doing SSL pinning or anything like that correctly, and falling back to plain text if something should fail, or if the use staging environment bit is set to 1 or something. So a real-world example, some researchers found that Google Client Login, which is the SSO system for pretty much all of Google's services, the authorization header was actually sent over plaintext HTTP on Wi-Fi when syncing for certain services like Picasa and Calendar and Contacts. So even though Gmail, for instance, was over SSL and everything like that, these services weren't. This was fixed by simply snipping this value on, say, a shared Wi-Fi network. You know the drill, super easy, whatever. I hate this case study, but it won't go away. Foursquared was a Foursquare application for Android, since been deprecated, but Foursquare is a location-based social network. I'm sure most of you are familiar with, and the API used to support OAuth or HTTP basic auth. Even though OAuth includes all these things to prevent replay attacks and whatnot, Foursquare, the Foursquared Android app used plaintext HTTP and HTTP basic auth. So, steal the wonderful little base64 encoded blob and check someone into Chippendales or wherever. Yeah, not really a big deal. You can check someone in somewhere else, but things like credential reuse kind of exacerbate this problem, and obviously, since most applications prefer Wi-Fi to cell radio, where possible, this is kind of a common issue. And incidentally, that application had OAuth support in, but the guy just didn't want to use it. I guess they've probably since used a different developer. Who knows? So, the advice there is any sensitive data or all data, if you can, because it's, phones are modern phones have enough power to do this, and bandwidth isn't a huge concern. All data leaving the device, especially if it's sensitive, should be encrypted, and it's not like rocket science to put a few extra lines in there to actually do proper SSL validation. And this includes over carrier networks, because you can't guarantee who is or isn't snooping on what's going across a carrier's network. And when security exceptions are thrown because of things like man-in-the-middle attacks, don't ignore those security exceptions and fall back to plain text. Maybe notify the user that something is awry and don't proceed. Insecure storage, of course, rooted device, all bets are off because it's a rooted device. They have, ACLs don't mean anything at that point. Android devices do isolate apps, data directories, as I mentioned before, and try to lock down permissions. If you leave USB debugging enabled, for instance, except on newer Android devices where USB debugging actually has authentication, that's a pretty good opportunity for, unfettered access to something. So just a little example application here where it actually stores credentials in this shared preferences file, and they actually went out of the way to shoot themselves by saying, shoot themselves in the foot by saying mode world readable and putting, username and a password perhaps in plain text there. So derp. The default mode for files that are created through Java, so databases, shared preferences, plain text files, any file that's touched through Java will actually be set securely with appropriate permissions. But anything that up until Android 4.1, anything created through native code, when you called into JNI and then did something or executed an external command, that would inherit Zygote's UMask of nothing, 0000, and subsequently set the permissions world readable and world writable. Again, this was fixed in Android 4.1, so Zygote actually has the same UMask now. This actually bit Skype in the butt because they had pretty much everything in their application was created through native code, including databases that had chat logs, had credentials, had personal identifying information about that particular Skype user. So as long as you could know what their username was, you knew that it was the files directory and then their username and then a bunch of files that were readable and writable by any other application. So store only what is absolutely required. Obviously, never use shared storage areas if you can avoid it, especially on older devices where FAT is the default file system that has no access control enforcement on that file system. Leverage secure containers, like Android has ASEC containers and has these OBBs or opaque binary blobs that actually provide a little bit more secure storage. And using things like SQL Cipher, if you have to use SQLite databases to securely store sensitive data. And don't go out of the way to shoot yourself in the foot by making world readable or world writable permissions on files when you create them. So information leakage through logs. Simply running ADB logcat on your development machine will often yield a wealth of information. Here's just an example of me clicking on a link in an SMS message and the activity manager, which subsequently launches whatever it is that will read or request and read a URL, HTTP URL. That activity gets logged. So not a big deal that someone can see that I tap on links all day and look at pictures of cats on the internet. But at least then, simple things like this are in fact logged. So it's a trivial example. Up until Android 4.1, applications could request the read logs permission, which meant they had access to the shared log buffer. And now, third-party apps are no longer allowed to do that, but on older versions of Android, obviously this still applies. So an example where this actually proved to be pretty helpful in an engagement, a Android app assessment engagement. We wanted to hack the thing that the app talked to but they actually did everything right around SSL cert validation and pinning, and made man-in-the-middling the traffic stream a pain in the butt. But they logged to the shared log buffer, to Logcat, the whole structure for the post message that we needed to be able to send to their web service to attack it, and it, of course, turned out to be massively vulnerable. So that was a nice little bit of information leakage. And just during a class this past weekend, we were playing around with a production app that we pulled from the market, which actually logged a token, we believe logged a token related to the user authenticating to this person's website right on the log. So any application could read that out and snarf that and put it somewhere else. So don't log credentials, don't log anything sensitive to shared log buffers or at all, if possible, especially not in production applications. If you're doing anything around logging, there were alternative keys for Android, which would actually log what keys are being tapped, and that would go to the shared log buffer. So there you go with your backdoor keystroke logging. Don't log those things. Utilize anti-caching directives on the back end for content that's being served to an application, because data does get cached for applications. They actually do have web content being cached for them in their data directory. Debug your applications, obviously. And any third-party libraries that you're using, see what they're logging, see if their ad networks, for instance, might be exfiltrating sensitive user data to somewhere else, including like contacts or PII. And test across as many platforms as possible, because there might be platform nuances or version nuances you don't understand. We had this storage application that we tested one time. It's multi-platform application where you can access your stuff on the web or through the Android application or whatever. And as it turns out, slight usability bug when intercepting the response from the server that would tell us things like our current storage quota by changing the current value that we used and the max value or quota. It would go and divide this to present like a nice little display, and would just lead to divide by zero error, as it, they didn't handle that, so the application crashes. Big deal. They did some DRM stuff as well, which wasn't really DRM, but this XML blob comes back from the server and would determine whether or not a video could be shared, but the decision was being made in the application itself, the client application that we have control over. So I want to go share this with you. Copyrighted, yes. Oh, I can't share it. Nope. So here's the XML blob that comes back. I change it from view to share. The access control decision is made in the client app, and suddenly I can share it with whoever. So DRM bypass, because it wasn't really DRM. So obviously not putting that logic in the client-side application itself, but enforcing it somewhere that you have more control over. So API-related issues. As I mentioned before, because of this isolation or sandbox, applications preferably interact with each other through an inter-process communication channel, if you will, by passing intent messages back and forth. And these are basically just objects that define things like what an action that an app wants to take, like view or main, and the component that it wants to send that message to. If it doesn't specify that, there may be an application that's the default or implicit handler for that, as well as any pertinent data. As we saw in that log output earlier, me tapping on a link, you saw dat equals, sourceconference.com. And since the scheme for that is http:// the web browser is the default handler for that. So, and then there's a reference monitor in the Android runtime which checks to make sure that everything is copacetic, that the caller and the callee jive with permissions, if permissions are being enforced for receiving or sending any of these intents. So generally, activities have to be exported for one application to invoke an activity or UI on another application. And setting an intent filter will do things like, handle a particular type of intent based on some criteria, like the scheme, the URI or protocol, or any other criteria that might be pertinent that a thing wants to receive. Developers can actually can require the callee to bear custom permissions to receive an intent, or the caller to require the caller to have a permission in order to send an intent to a receiver. So these can be further restricted, and ideally are, by first creating a custom permission and then also setting protection level equals signature. What that does is says that only any application signed by the same key as the application that declared this custom permission can request this custom permission. There's also signature system, but that also opens it up to OEM and Google applications as well. So if you don't want to trust them, don't set things like signature or system. This kind of could potentially break compatibility in some cases, but invoking explicitly specifying the target component that you want to send in a message to is better, because then an application cannot register to be a higher priority intent receiver for something that you didn't expect it to be. So here's an example, really convoluted but valid example for starting an activity. We say we've got an intent message called foo. We want to invoke the action view, the view action. We set the data to be bar : / some resource. Let's assume there's a protocol called bar, and we just start activity foo. And what this does is just says, I want to view, and here's the data, and whoever can handle that can handle it. So if your application that you have this special custom protocol or scheme for handles bar, but some other malicious application registers as a higher priority intent filter to receive and handle the bar scheme, it would intercept this message first. This would explicitly specify the component we want to receive this message. So we say, same thing except set component com.mycompany.myapp.myactivity, and the message is sent explicitly to an application we know and a component, an activity that we know. So applications can also register broadcast receivers, which are broadcast messages, things like SMS received. The telephony manager sends out a broadcast message to anyone who will listen to notify that an SMS has been received. And that's how the messaging app intercepts that and responds to it accordingly, and how custom SMS messaging apps deal with it as well. They just register as a higher priority intent receiver. So the principle of permissions applies here. You can require the receiver to bear a custom permission before the message will be delivered and consumed by them, and vice versa. The receiver can also require that the caller bear a permission to even talk to it. Use permissions wisely and often, but generally, if you are not doing that, don't just send highly sensitive data in a broadcast message that anyone could register a receiver for. Don't forget that intents are actually an input point, and sanitizing input and controlling access to messages you receive and messages you send and who will receive them is important, and also handling exceptions is really important. So ISEC Partners, for instance, has this real application called Intent Fuzzer, which just enumerates everything that can receive an intent: activities, service, broadcast receivers, and instrumentations, and just sends null objects to them to see what happens. So it just it says null fuzzing. So it just sends null objects and everything crashes, including Google's own services on Android. So we see here the clock that was provided to me as a stock application crashes, alert service crashes for a null pointer exception. So pretty much everything crashes here. Third-party applications fall to this, and Google's own applications fall to this because they don't handle null pointer exceptions. So speaking about not using IPC mechanisms properly and kind of shooting themselves in the foot, we had an engagement that we did where we tested a while back, this custom app framework. Think of it like a write once, run anywhere across, Windows Mobile, BlackBerry, Android, etc. And it was basically just HTML and JavaScript widgets like games and stuff. So we actually couldn't talk to it was composed of two components, a widget installer and a widget runtime. And we wanted to talk to either of them through passing intent messages. Well, the widget installer even wouldn't let us send messages to it and invoke we couldn't like fish a user to get them to install our malicious widget, because we couldn't even invoke that activity because we didn't have the appropriate permission. Only the widget runtime and some other applications, like system applications, had that. So we actually see it's a little redacted, sorry. But you see protection level, signature, or system for this permission in this permission block in the manifest. We just try to use the activity manager to invoke view. We pass in some MIME type data and a path to our widget. And we tell the widget install activity to pop up to prompt the user to install our widget, and we get permission denial because we don't have whatever that permission is. Well, that sucks. Well, as it turns out, they didn't understand things like shared UID, where two applications signed by the same key can share user ID and access the same parts of the file system. So they just made their widgets directory world writable so that the two UIDs for the installer and runtime could read and write that directory, which meant anyone else could write that directory, which meant our malicious application could overwrite widgets and add in content, which is what it did. So if you look at the permissions here, you'll see read write X, world writable, world readable, and we have a chess widget, which was world writable and world readable, and our app that just injected content so that when the user opened it, it just had a JavaScript pop-up. So again, they didn't couple the widget runtime with the widget management application via IPC. There could have been a programmatic way to do this without, botching it on the file system. And they sidestepped the permissions model by doing really bad old Unixy file permissions management. So to conclude my whirlwind tour of Android application security dumbness, don't store sensitive data, especially in plain text and without proper access control. Be aware of system nuances, things like the Zygote UMask inheritance issue for native code, and any memory issues if you have native code and you're deploying on like Android 1.5. You probably opened it up to more vanilla, exploit issues, vanilla buffer overflow vulnerabilities, maybe. But just know that there are basically no exploit mitigations there. Think about what permissions an application really needs. Don't request more than necessary. Unless you're a mobile AV application, then you have to, apparently. And any security facilities provided by the platform, like ASEC or secure containers or crypto libraries or pretty much anything, be aware of them and use them. Don't necessarily roll your own unless you're really good at it. And everyone's always really good at it. And just remember that anything you build on may have its own issues. Flash, WebKit, OpenSSL, Bionic, libc, so forth and so on. So there's also the OWASP Mobile Security Project, which is attempting to bring together resources around mobile application security in particular, but also just mobile security in general. So you can go there and get involved and get spammed on the mailing list by some guy who posts a bunch of off-topic things. It's not me. Any questions? I have about 5 minutes. There's my contact information and stuff. All right, I'll take that as a no. Well, thanks for putting up with the alternate presentation for this slot. Thanks for coming out to Source. And if you have any questions, feel free to come up here and talk to me for the next few minutes, or out in the hallway track. Thanks.